please.
Okay, so welcome this morning for the seminar from Professor Devolder, most of you know here. He's from Université Paris-Sud and expert in FMO and high-frequency spectroscopy, magnetic spectroscopy. And today we'll talk about Gilbert damping in iron, cobalt, boron, MgO systems. I leave the floor to you.
Thank you, Sébastien. And indeed, it's a pleasure for me to be here once again. So to present a seminar about my views on how to understand the Gilbert damping in iron cobalt systems. Okay, and this is a joint work with collaborators. Most of them are located here, so they will recognize themselves in the list. Okay, and also from my colleagues at the Université Paris-Sud, Juvon Kim, Jean-Paul Adam, and also a student, Paul Bouquin, who is shared between IMEC and my group. Okay, so I used to belong to a lab that was called Institut d'Electronique Fondamentale that lived for 50 years. I was not there at the beginning, but only in the last 20 years. Okay, and it suddenly disappears to be transformed into a new lab, which is called the Centre de Nanosciences et de Nanotechnologies, which was founded last year. Okay, and we're supposed to move in this new building early this year, which means early in June. Okay, and it's going to be it's going to be a member of the new university, which is called Université Paris-Saclay, which gathers many institutes and research labs in the south of Paris. Okay, but my objective today is to describe what I understood in my studies of damping in iron cobalt boron systems. Okay, so my talk will be divided in three parts. After having described shortly what is Gilbert damping, I'll try to give the qualitative pictures that are needed to understand this physics. Okay, and then I will, in a second part, I will go specifically to one material system that is very popular in spintronics, which is cobalt iron boron on MgO films. Okay, and in the last part of my talk, I will also study the damping, but describe what we can do at device level. Okay, so why damping matters? If you take a ferromagnetic body, okay, if it's ferromagnetic, it means the ground state is with the spins that are parallel and at rest. Okay, and the excited states of these systems are what are called the spin waves. Okay, so it's precession of the magnetizations with a wavelength and a frequency, but it's an excited state, and so it will decay in time, and the process by which the spin wave decay is governed by a quantity that is called the Gilbert damping. Okay, and this decay of the spin wave implies two effects. One, that the energy of the spin waves have to leak away from the magnetic system, so it has to leak to the thermal bath. Okay, and also the angular momentum that was carried by the spin wave has to be carried away also. Okay, so damping is essentially the rate at which the magnetic energy is lost from the magnetic degrees of freedom to the rest of the world. Okay. And it matters for many applications because, for instance, if you use magnetic memories, what you want to do is switch the magnetization. If you're using magnetic sensors, for some of them you need to have the magnetization to rotate. In oscillators, you want the magnetization to precess. Essentially, you want the magnetization to change in many magnetic applications. And damping is the torque that will oppose to these changes. Okay, so understanding the damping is very important for many applications. And for instance, for spin transfer torque magnetic random access memories, we work with small, tiny nanomagnets. Okay, and the way we switch the magnetization is by amplifying a spin wave before the magnetization reverses. And the voltage it costs for this switching is directly proportional to the damping parameter, also to other magnetic properties, but to the damping parameter. So if you can minimize this parameter, you will minimize the energy cost of the reversal. Okay. Some numbers. In very pure single crystalline iron, the damping is something like 2 to the 10 to the minus 3, while in devices is typically 10 to the minus 2. Okay, so substantially larger. Okay, and so understanding how to reduce the damping is very important because a lot of energy is wasted in devices because this damping is higher than in the best materials that would be available. Okay. Generally, we measure the damping parameter by ferromagnetic resonance techniques, okay, and the modern version of it, which is vector network analyzer ferromagnetic resonance. Okay. The idea is the following. Okay, you prepare an RF strip line, okay, and you characterize the impedance of the strip line with a vector network analyzer. Okay, so the impedance of the strip line is influenced by the permeability of vacuum. Okay, but if you replace the vacuum that is around the strip line by a magnetic sample, you will add an extra permeability. Okay, and so if you can frequency analyze the impedance of this ensemble, the sample plus the strip line, then this contains information about the permeability of the sample. Okay. So from this you can extract the real part and the imaginary part of the transverse permeability of a magnetic sample. This is, for instance, what can be obtained on a free layer of an STTMRAM cell. Okay. And this permeability spectra versus frequency, they contained two information. The field at which the system resonates is a measurement of the strength that holds the magnetization, so it's the applied field and the anisotropy of the system, while the width, the line width of the resonance is a measurement of the Gilbert damping, so a measurement of the rate at which the energy decays to the non-magnetic degrees of freedom. So generally we measure the damping not only of one layer, okay, but we work with complex systems. Okay, so this is for instance a stack that was used some time ago for STTMRAM application, where essentially you see that you can have up to, in this case, 4 magnetic blocks. Okay, and if you just do conventional magnetometry on this system, that is to say, if you measure a hysteresis loop, so magnetic moment versus field, it tells you already that what are the easy axes of magnetization of the system, if they are soft or hard, but it doesn't tell you numerically what are the properties. Okay. So if on each of these ground states that you can prepare by a static field, you could measure the eigenmodes of the system, then this would tell you more. And this is what we do by VNA FMR. Okay, so now you have a graph where for each applied field here in abscissa, you scan the frequency from 0 to 70 gigahertz, okay, and you see a number of eigenmodes that appear as resonance in the permeability spectra. So for instance, in this sample where you have 4 magnetic blocks, but you were only seeing 3 different switching in the hysteresis loop, you still see in the eigenmodes that you do have 4 eigenmodes because you have 4 magnetic blocks. Okay, and if you spectrally analyze this ferromagnetic resonance frequency, that is to say, if you make vertical cuts on this graph, okay, you can, for instance, make a vertical cut here where you will see a narrow ferromagnetic resonance line indicative of a layer with a small damping. It's the free layer. Okay, while if you go to higher frequencies, okay, you can look at the resonance frequency of the harder parts of the stack, and this is, for instance, the acoustic mode of the platinum cobalt multilayer in this system. Okay, and by this you immediately see that because it's a spectroscopy technique, you can address the part of the stack that you want to address simply by selecting the field and the frequency conditions. Okay, so this is the standard way of extracting the damping. So from the line width of the ferromagnetic resonance. Unfortunately, in many systems, the line width is not only influenced by the intrinsic Gilbert damping, but it's also influenced by the microstructure. Okay, because we're most of the time working with layers that are sputtered deposited and that are polycrystalline. Okay, so imagine you have different crystallites in your systems with different anisotropies, either high anisotropy areas, low anisotropy areas, and grains with an intermediate anisotropy. If you measure the permeability of this sample, you will see a line width that's going to be the addition or the spatial average of all these local resonances. Okay, so you will end up with a line width that is a composite of the dispersion inside the samples. Okay, and that is what is called ferromagnetic resonance inhomogeneous line width broadening, which you also have to account when you look at FMR spectra. Okay, so this is the way we measure Gilbert damping, so by ferromagnetic resonance. Okay. Let's now try to describe what is Gilbert damping. Okay. Okay, so Gilbert damping is essentially the decay of a spin wave in a magnetic systems. So if you want to annihilate a spin wave in the magnetic material, you need to obey some conservation laws. You need to carry the energy away, you need to carry the wave vector away, and you need to carry the angular momentum of the spin wave away. Okay, so you need interaction with other degrees of freedom. So in practice in metals, the other degrees of freedom that you have are the electrons. Okay, so you need to have electrons ready for interactions, so they will be at Fermi level. Okay, and you need to have empty spaces for the electrons to be scattered into. So this is going to be also electrons at the Fermi level. Okay, so in practice in metals, if we now put the numbers for a spin wave to electron interaction, okay, you will see that the spin wave, usually we work with magnetization dynamics frequency, so we will consider magnetic excitations of a few gigahertz, which in terms of energy is 0 compared to the energies of the electrons at the Fermi level. Okay, so I will say 0 energy. Okay. We also generally were interested by magnetization dynamics, long-range fluctuations of the magnetization, so not atomic scale variations of the magnetization. Depending on our device size, we will be interested in the low part of the K vector. Okay, but essentially, I will also say that we're interested by what happens at almost 0 wave vector. Okay, so if the spin waves interacts with a conduction electron, okay, it will transfer some wave vector to the Fermi level electron, but the wave vector that has to be transferred is very small, such that if we speak in terms of direction of the electron, the electron is not much deflected. Okay, and the energy of the electron stays the same almost, so it stays at the Fermi level. The only thing that changes for the electron is that it has to carry away the angular momentum, so the spin of the electron will flip. Okay. So if you want to understand damping in metals in this interband picture, what you have to look is you look at the Fermi level of your metal, do you have bands with spin up and spin downs that cross? Okay, so if they cross, there will be a 0 energy and the 0 wave vector transition that will be allowed. Okay, so let's first look at half metals, keeping this picture in mind. Okay, half metals are metals in which you have a gap in the minority band at the Fermi level. So these are systems where if you look at the density of states, near the Fermi level, there is no minority electrons. So if you would try to apply this process to a half metal, you would take a Fermi level electron, okay, so a black electron, okay, and you would try to put it at the Fermi level with the opposite spin. So you would try to put it in a box, in an available box that is red. Okay, but obviously this process is not possible in half metals because there's no states to be scattered into for the conduction electron. Okay, and that's essentially the reason why half metals have dampings that are much lower than ferromagnetic metals. Okay, remember that in standard metals the damping is typically 10 to the minus 2, and it's at least 10 times less for good half metals. Okay, and even smaller in calculations for ideal materials. Half metals are not the most practical for spintronics. We generally work with standard ferromagnetic metals. This is, for instance, the case of iron. Okay, and for iron, at the Fermi level, you both have spin up and spin down electrons. Okay, so in this picture of magnon electron scattering, okay, you could imagine that some processes are allowed. Okay, at least energy-wise and spin-wise. So you have to look at whether it's possible in terms of conservation of the wave vector. So for this, you need to look at the band structure of iron. Okay, and here I'm only plotting a part of the band structure of iron in the gamma H direction of the first Brillouin zone. So this is the direction that matters for transport in a tunnel junction. Okay, and if you look at the Fermi level, this is here. okay, what you can see is that there's no crossing of spin-up and spin-down bands in this part of the first Brillouin zone. So if there was only this part, you could not find a process that could be responsible for magnon electron scattering in these metals. Okay. Of course, this is only a part of the first Brillouin zone, so we need to look at the full structures. Don't be scared, I will show the full band structure of iron, okay, and also the full band structure of nickel. Okay, and the part that I was showing before was this just this small violet box here that was zoomed in. Okay, if you go on looking at the Fermi level, this is this white dotted line. You can see that definitely there is no band crossing at Fermi level for spin-up and spin-down bands for iron. Okay, while if you compare it to nickel, okay, which is not BCC but FCC, if you look especially here, and I'm going to zoom on this point of the Fermi surface, okay, so this is the Fermi level. What you can see is that there's a spin-up band and a spin-down band, the black and white bands, that cross at the Fermi level. So this is really a transition that is a potential killer for damping, and that can generate a large damping. Okay. And effectively, the damping of nickel is 45 10 to the minus 3, okay, which is 20 times larger than that of iron. Okay, and the main reason is this availability of this transition in one case and not in the other case. Okay. This large value of the damping of nickel is the reason why not many people use nickel for microwave applications of magnetism. Okay, instead they will use permalloy. Okay, so they will substitute some of the nickel atoms with iron atoms. And if you do that, if you remember the periodic classification of elements, if you replace a nickel atom by an iron atom, which is on its left, that is to say that you're removing electrons from the systems. Okay. If you're removing electrons from the system and the crystal structure stays the same, essentially you can consider that the band structure is rigid, but what you do is you lower the Fermi level because you're removing electrons from the system. So if you go from nickel to permalloy, you will have a new Fermi level that will be this yellow line here that will be below the Fermi level. And in fact, these two bands, they gradually separate. Okay, when you go down in Fermi level, and that's why the damping of permalloy is indeed 7 instead of 45, so it's substantially better. Okay, but be careful if we were to go on decreasing the Fermi level by substituting even more iron. Okay, we would potentially hit these transitions. Okay, and that's maybe one reason why. For iron-nickel alloys of higher iron content, the damping is larger. Of course, this picture makes a very crude approximation, rigid band, and assumes that the exchange splitting doesn't vary with the composition, so it's only qualitative. Okay. But I want you to remember that most of the difference between nickel and iron doesn't come from a difference in spin orbit. Okay, they are approximately the same. Okay, the difference comes from the details of the band structure. Okay. In applications, we are much more in spintronics. We are much more interested in iron and iron cobalt systems. Okay, so I will now come back to iron. Okay, and I will zoom on this part of the band structure. Okay. Once again, for pure iron, the Fermi level is this white dotted line, and there's no band crossing at Fermi level. But if you substitute iron with cobalt, okay, cobalt has more electrons, so what you do is you're raising the Fermi level up, okay, and if you raise the Fermi level too much, you will hit that transition where there is a band crossing of spin-up and spin-down bands. Okay, and this is happening essentially if you put more than 50% of cobalt in the structure. Okay, and it's well known for years now, this was before I started my PhD, so it's old data, that if you look at the damping in iron-cobalt cis-binary alloys, okay, if you stay below 50% of cobalt, the damping is very good and very similar to the one of pure iron. Okay, while if you enrich too much in cobalt, okay, indeed the damping is increasing. And this is an intrinsic effect, and this is also something that was measured in thin film. Okay. Well, so that's an intrinsic picture, a picture of intrinsic damping. Okay. In practice, we work with thin films, okay, and they have damping that are substantially larger than the bulk counterparts for the same compositions. So that's one first statement. And the second statement is that when you receive a sample, the nominal composition of the sample doesn't really tell you what damping you will have. Okay, so for tantalum, iron, cobalt, boron, MgO, okay, this is a very standard structure in spintronics. Some suppliers will give you layers with the similar composition, and they will have damping that will vary very much among these sets of sample. Okay, so there is a lot of variability in samples. Okay, and this brings me to a discussion about the spin-orbit coupling and the role of impurities in metals. Okay. So far, I only described the interband picture of Gilbert damping. There's another effect that I want to explain, which is called the breathing Fermi surface picture. Okay, and where it's the intraband transitions that are responsible for damping. Okay, and for this, I will consider an ideal metal with no spin orbit on the upper part and with a strong spin orbit on the bottom part. So we look at the Fermi surface. We put electrons at the Fermi surface and some initial magnetization. Okay. And then imagine you excite a spin wave, so magnetization varies in time. Okay. So if magnetization varies in time and the metal has no spin-orbit coupling, there's nothing specific happening for the Fermi surface. The electrons is still on the Fermi surface, it's happy to be there, there's no enhanced scattering or whatsoever. But in contrast, if the metal has a strong spin-orbit coupling, when you rotate the magnetization is locked with the Fermi surface. So it deforms the Fermi surface substantially, while the electron has kept its momentum. So you end up in a situation where if the magnetization evolves and there is strong spin-orbit coupling, then the electron is put away from the Fermi surface, so it will want to make efforts to repopulate the Fermi surface, and there's going to be an enhanced scattering probability responsible of damping. Okay, and this process is more probable if the lifetime of the Bloch state of the electron is long enough so that magnetization can vary. So it's a process that is proportional to, let's say, the conductivity of the material. And that's this process that is responsible for the very strong increase of the damping of iron, for instance, at low temperature. Okay. And in the intraband picture that I was showing before, the spin orbit is also responsible for the transitions. Okay, so far I only talked about the transition from one band of spin up to one band of spin down, but I said that we needed states at the Fermi surface to allow this. But I did not talk about what was the matrix element that was responsible for these transitions to happen. And it's the spin orbit coupling. Okay. And this is very important, okay? And there's a very good illustration of this in a paper by Ronschler and co-workers, where essentially what they did is they took permalloy, okay, and they systematically doped permalloy with transition metal elements all over from the periodic classification, okay. And the size of the bar in this graph, where's my mouse? The size of this bar is a measurement of how much the damping increases if you put a certain percentage of dopant in the material. Okay. And what you can directly see is that if you dope with 3D elements, this is less detrimental than 4D elements, and this is much less detrimental than 5D elements. Okay, and this is just an illustration that spin-orbit coupling matters, as it increases substantially if you go down in this table of elements. Okay, and you can note that there is a strong maximum at the middle, and I'll come back to that point when I will discuss experimental data on STTMRAM free layer. So a strong maximum at the middle of the transition metal series. Okay. Another illustration of the effect of dopant. Let's imagine you can do the following experiment. You can start from an ideal system where you have your ferromagnetic layer on top of a heavy metal. In the practical case, it's going to be tantalum. Okay. If you can controllably mix the interface, and for instance you can do by ion irradiation following a method that was pioneered by my supervisor some time ago, so this is now well controlled. Okay, you can do this intermixing in a, let's say, in a very controlled way. You can know how much dopants you have in which layer and so on. Okay. And while you are doing this gradual mixing, okay, you can follow the magnetization of the system and the damping of the system. Okay. First look at the magnetization versus the amount of mixing in the system. Okay. What you can see is that the magnetization is not that much sensitive, okay, to the intermixing. You see a decrease, okay, what people would interpret as a dead layer, for instance, okay. But before you see a very substantial decrease, okay, you see a substantial increase of the damping, a dramatic increase of the damping in the system, and this is a factor of 3. Huh? Okay. So my message is, as soon as you have dead layers in these systems, okay, you know that if you have dead layer, and this is generally observed in tantalum, cobalt, iron, boron systems, you expect that you've already degraded your damping substantially. Okay, so if you see a dead layer, it means you can optimize structurally your sample and you will gain in damping. Okay, so either you replace tantalum by something else or you avoid mixing at the interface. Okay. And with this brings me to the second part of my talk, where I will specifically discuss the case of iron, cobalt, boron, MgO films with out-of-plane magnetization. Okay. These systems are generally used for tunnel junctions, and for tunnel junctions we want a given material structure. And the structure we want is typically this one. We want a crystalline MgO and a crystalline iron cobalt with a perfect epitaxy between these two, okay, because this is needed to achieve the giant tunneling magnetoresistance. Okay, and you also don't want any intermixing between the capping layers and the ferromagnetic layers, as I mentioned before. Okay, and if you manage to have this structure, you're going to have a very good tunneling magnetoresistance and a very low damping. When we deposit the sample, we have to deposit them in the amorphous state for technological reasons. So we start from a situation where we have a low TMR and a reasonably low damping if there is no intermixing. Okay, and ideally we would like to change from the as-deposit case to this ideal structure, but in practice, when we anneal the system to crystallize, we get samples that typically look like this, where you're going to have a roughness at the interface between the cap and the magnetic metal, and you're going to have some interdiffusion, and this will degrade the TMR and the damping. So you essentially have two problems to solve. One is roughness, or generally structural disorder, and the second one is intermixing. Okay. So let's talk about the roughness, since the method to cope with this situation was developed here by Johan Zwert and co-workers. If we do conventional growth, okay, so we have iron, cobalt on MgO in the amorphous state, okay, and then we want to deposit, for instance, tantalum on top. Okay, so the tantalum atoms are very heavy compared to iron cobalt atom, and it's a sputtering technique, so the typical energy of the impinging tantalum atoms will be something like 50 eV, which is substantial. Okay, so while you deposit the tantalum, this will partially sputter away some of the iron cobalt atoms. Okay, such that in the end, after the deposition of the tantalum layer, some iron cobalt atoms have disappeared, so you measure less moment than what you expect from your deposition rate. Okay, and so this is generally assumed to be a dead layer, so dead layer means everything. Okay, but in this case it means you measure less moment than what you expect. Okay, and you also have tantalum implants inside the iron cobalt layer. Okay, So the method that was developed here by Johan Wert and co-workers was to develop a sacrificial Mg layer. Okay, and the idea is that it's light atoms, so they are easily sputtered away when you deposit the tantalum. And if you put the correct quantity of Mg atoms, at the end of your deposition, you've removed all of them, or almost all of them. Okay, and so you have no dead layer. So you recover the nominal magnetic moment and a rather smooth interface. And indeed, if you measure the RF properties, if you compare the RF properties of the samples deposited in these two ways, there is a substantial difference. So let's measure them after annealing at 300 C. If we look at the damping, there's really not much difference. It's within the error bar, especially at that time where the damping measurements were not very precise. Okay, but there is a substantial difference if you look at the non-uniformity, as you can measure it by the FMR line width broadening. And indeed, the samples deposited the conventional way have a non-uniformity that is substantially larger than the one that you measure on the samples with a sacrificial layer. So there is a strong benefit of doing this. Okay. So let's say structural disorder, there is a trick to reduce it. Okay. Then the second trick I want to talk about is why we should engineer the boron content in the iron cobalt boron layers, and why would that affect the damping. And this is not direct, but this comes from the thermal budget that is used to prepare the sample. Ideally, we want to start from the as deposit state, which is amorphous, okay, and we want to end in the ideal crystalline structure. And for this, there's no negotiation possible with CMOS people. You have to use 400 C annealing. Okay, there's no way you can avoid this. Okay, so the crystallization happens. The material evolutions happens in two steps. There's a first step, which is the one you want, which is the crystallization. And the crystallization temperature will depend on how much boron you put in the system. And this is just like in any glassy metal, the crystallization temperature depends on the amount of metalloid that you put in the system. Okay. But unfortunately, once the sample, before the sample crystallizes, there's not much interdiffusion. By definition, an amorphous material is a one in which the atoms have no mobility. If they had mobility, they would crystallize. So before it crystallizes, there's not much interdiffusion happening. So right after crystallization, you can assume that you have a good interface with not much intermixing. But unfortunately, the annealing lasts longer and to higher temperatures, so there is interdiffusion. Okay. Because this is done at 400 C. Okay. So what you would like is to get rid of the second step. Okay. And for this, the trick that has been developed here is to increase the boron content as much as possible to try to have a crystallization temperature that is as close as possible to the 400 C that you need. And if indeed you can engineer the boron content to match these two temperatures, you will not let time for the systems to interdiffuse, and you may end up in an annealed state that is much less interdiffused. Okay, so the strategy is really to postpone the crystallization till exactly 400 C, and if you manage to do that, you will minimize interdiffusion. So to see whether this is effective to reduce the damping, IMEC people prepared samples for me with the following compositions. So essentially these two samples differ by the amount of boron that is put in the ferromagnetic layer. You have approximately the same number of iron cobalt atoms in these two systems, but they differ substantially by the boron content. And what is done is an annealing at 400 C, and after that we measure anisotropy, we measure array, TMR, and so on. If we measure TMR and array, and also anisotropy by FMR, there's not so much difference. But if in contrast you look at the line width of the ferromagnetic resonance, which is influenced by the damping, you can directly see, I mean visually this is striking, then the sample with the highest boron content is substantially better in terms of damping. Okay, and the likely reason is that there is much less tantalum contaminant in the iron cobalt boron system. If we extract the damping from this line width, okay, for 30% of boron, the damping is something like 9×10⁻�3, so substantially below the one for 20% of boron. Unfortunately, this is still much above what could be obtained on pure iron or pure iron cobalt crystals in a single crystal state. Okay. So we are in a situation where most probably there is still dopants, heavy metal dopants in the system. Okay. And so assuming that the problem is that we still have some tantalum atoms interdiffused in the structure, okay, we'll try to reduce the number of potential heavy metal contaminants in the system. Okay. And for this, we will compare dual MgO and single MgO systems. Okay. So we will compare samples that are essentially like that. The previous generation, where the iron cobalt boron layer was sandwiched between MgO and tantalum, and a new generation of what is called dual MgO free layers, where the iron cobalt boron layer is sandwiched between two layers of MgO. Okay. And for technological reasons, we have to put a spacer in the middle of the iron cobalt boron layer. This is for crystallization purposes because the system crystallizes from the MgO interface towards the inner part of the iron cobalt boron layer. So it crystallizes from the two interfaces, and you have to put some glue in the middle so that everything goes smooth when the two crystallization front meets each other. This is very qualitative, but effectively this is needed. No spacer, no PMA. Okay, so let's compare the damping of these two systems once again by ferromagnetic resonance. So here I'm showing the ferromagnetic resonance of a single MgO free layer, and this is for the dual MgO free layer. Okay, and once again you also immediately see that there is a benefit. Okay, and if we now plot the line width versus the frequency in this last graph, the slope is the damping, and we are now at a damping that is something like 4. 10⁻�3, while we were at 9 before. Okay, and as you can see, we are now not that far from perfect single crystals. Okay, so indeed the damping of STTMRAM free layer now are not that far from the best achievable in iron cobalt boron systems. Okay, I mentioned that we have to minimize the number of contaminants. Okay. So we did a study on what is the optimum thickness of the spacer layer, the tantalum spacer layer at the middle of the free layer. Okay, so Johan Zwert and Sébastien Coué prepared a series of samples with variable tantalum spacer thicknesses, and I measured the damping, and as you can expect, the damping is increasing with the tantalum thickness in the middle. Okay, so this is another confirmation that essentially the number of contaminants that you put initially in the structure, okay, is the key factor to determine the final damping that you will have after 400 C annealing. And last, before I go to devices, I would like to comment on the choice of the spacer layer in the middle of the free layer. Because there's a lot of reports in the literature where people claim that tungsten spacers are better. Okay, but these people that claim this, most of the time they only measure standard magnetometry. Okay, so they only measure an isotropy and sometimes TMR. Okay, but this is not the only factors. Okay, and the energy cost of the reversal scales proportionally to the damping. Okay, so we measured the damping for various spacers. Okay, so this is once again by ferromagnetic resonance, and you also immediately see that tungsten spacers, they yield broader line widths than tantalum spacer, all other parameters being the same thicknesses. Okay, so definitely tantalum spacers are much better if we consider the damping as a criterion. Okay. And if you remember this paper that I showed by Ronschler and co-workers, where I told you that the effect of dopant is maximum on the damping if you're at the middle of the transition metal series, okay, you shouldn't be surprised that tungsten is indeed much worse than tantalum. Okay, tungsten has more d electrons, so it must have a larger effect on the damping. Okay. And with this closes the second part of my talk, where I only talked about films. Okay. And now I will detail what we can say and what we can measure at device levels. Okay. And most of this was done on samples provided by Vladimir Nikitin at Samsung. Okay. And what I will do is I will do a spin wave spectroscopy. Okay, so instead of doing ferromagnetic resonance, where we were looking at the uniform modes, okay, now we'll look at non-uniform modes localized in the free layer. So you have to assume that the free layer is patterned in a circular device with a ground state magnetization pointing up, okay, and now the spin waves are confined by the geometry, okay, so that you can have several spin waves, okay, just like the eigenmodes of a membrane, where you will have a quasi-uniform mode and non-uniform modes with either azimuthal index or radial indices. Okay, and the frequencies of these eigenmodes will depend on the degree of inhomogeneity of the magnetization. Somehow, there are analytical theories for the frequencies of these spin waves. These analytical theories do not work quantitatively, but they describe qualitatively well what is happening. And the frequency of these modes depend also on the anisotropy, on the demagnetizing term, but the leading factors that discriminate the frequencies of these different eigenmodes, okay, is the exchange stiffness, okay, of the material. Okay, so I'll try to measure this. Okay. So VNA FMR is not sensitive enough to work at device level. Okay, so when we go from films to devices, we will replace the RF field that was used for FMR by an RF spin torque that is localized on the device, and instead of measuring the permeability, we'll simply measure the tunneling magnetoresistance. So the experiment is simple, at least on the paper. You select a field, you select a frequency, you send the RF through your device, okay, and you collect the rectified voltage. So you send a voltage. If the resistance is varying with time, so if the system hits a spin wave, the resistance will resonate, and if it's not at resonance, you will not measure any TMR. Okay, and very important, you have to do it the French way, because that makes your life easier. By the French way, I mean that you have to choose that the free layer is magnetized opposite to the reference layer. Okay, so you prepare you prepare the junction in this anti-parallel state. And the reason for doing that is that when you measure spin wave spectra, so now that's frequency versus field, and the intensity is black when you hit a spin wave mode. If you work in this French configuration, it's very nice, because the FMR of the free layer is increasing with the field, while the FMR of the reference layer is decreasing with the field, just because they are anti-parallel to each other. So you immediately see from the mode spectroscopy what layer you are really analyzing. Okay, and in addition to the uniform modes of the reference layer and the free layer, you also see a bunch of spin waves in between. Okay. To analyze the line widths of this spin wave spectra, you essentially need to be able to identify each spin wave mode. Okay, and for this, you need the spin wave modes to be sufficiently separated. So if I make a vertical cut, okay, at some field, so I'm looking at this signal, which is going to be something like the derivative of the density of state of spin wave in my device. If I do it for a very big device, this structure is very agitated, and it's very difficult to say what are the spin wave frequencies. Okay, but if you reduce the dimensions of the nanopillar, okay, you increase the confinement so the modes separate from each other. Okay, and if you're using devices that are small enough, the spin waves are really separated enough so that you can look at them individually. Okay, so the optimal device size is typically below 100 nanometer. Okay, so let's do the analysis for a device of 90 nanometer. Okay, so we are looking at field scans at constant frequency or frequency scans at constant field, okay, of TMR. Okay, this should look like this curve in some modeling. Okay, and this is indeed the case at zero bias, and at finite bias they should have a different shape that should change with the sign of the voltage, and this is indeed the case. Okay, so if you have a spin wave signal and it verifies these four conditions, then you can reliably fit the line shape and extract the damping. And for instance, for these devices, the damping was 11, while for the films it was 8. Okay, so nothing very surprising. Okay, but in fact we can extract more information from spin wave spectroscopy. So let me come back to the eigenmodes of the system. And so far I only discussed the lowest order eigenmodes. Okay, but if you go to more non-uniform eigenmodes, so this is for instance the expected mode geometry for a mode with an azimuthal index 7. It means the spin wave makes 7 phase rotation upon rotating in the system. This looks very much like if you had a localized spin wave that would just travel near the edge of the pillar. Okay, so you can imagine that if you're looking at this mode, you will essentially be sensitive to the properties near the edge of the pillar, while if you're looking at a more uniform mode, you will be sensitive to everywhere. Okay, so somehow my message is that if you are able to compare the properties of these different modes, you will be able to somehow look at the Fourier transform of the spatial distribution of properties in your system. Okay, so and I will do it for the 3 first modes. Okay, so here I'm plotting the line widths divided by the frequency. So that's somehow the effective damping versus field for the second and third modes that are measured in these devices. Okay. And if you look at the damping that could be extracted from these 2 modes, they are equal, okay, within the experimental uncertainty. Okay, and importantly, these are azimuthal spin waves, so the precession amplitude is 0 at the middle of the disk by symmetry for these 2 spin waves. So they do not sense the center of the device. Okay. If in contrast I look at the most uniform mode, okay, a mode that would have this geometry, okay, then if I look at the damping parameter that can be extracted, there is a lot of noise, but indeed it seems to be a bit smaller. Okay, and so the difference between these 3 modes is that they do not sense the same regions within the device. The 2 first are not sensing the center, while the last one is sensing the center. Okay, so from this I would say, since these 2 have the same effective damping, there is no dependence on the K vector, or at least it's not observed in my devices, contrary to what other people have observed in larger devices made of permalloy. Okay, but for me, the main difference is that indeed they sense different areas, so you can use spin wave spectroscopy to have a qualitative understanding of the radial gradients of the properties in devices, and this is a tool that somehow we should think of using more systematically. And this brings me to my summary. Okay, so in the first part of my talk, I've explained qualitatively what is the Gilbert damping, and what I want you to remember is in ferromagnetic metals, most of the damping comes from the collisions between the spin waves and the conductions electrons at the Fermi level. And for this process to be allowed, you need to have band crossings of spin up and spin down bands. Okay, so the details of the band structure matter. It's not going to be the same if you deposit in BCC or FCC state. Okay. And I've illustrated this fact on cobalt iron alloys and iron nickel alloys. Okay. Spin orbit is also a key ingredient. Okay, as you can see, when we mix a ferromagnetic metal with a high spin orbit cap, this degrades very substantially the damping. So from these qualitative pictures, we could design solutions to reduce the damping in iron cobalt boron systems. First, by using smart deposition techniques to reduce disorder, then by engineering the boron content to minimize the interdiffusion, okay, and then by carefully choosing the thicknesses of the potential contaminating layers. Okay. And in the last part, I measured the damping at device level. Okay, so I developed a method to do that as reliably as possible, and I tried to apply on the spin wave spectroscopy to see what we can gain in terms of understanding. And with this, I thank you for your attention.